By the laws of physics as we understand them, none of this should exist. Not the stars, not the planets, not you. The Big Bang should have erased itself completely an instant after it happened. And physicists still don't fully know why it didn't. Here's the problem. Every equation we have says the Big Bang should have created matter and its mirror opposite, antimatter, in exactly equal amounts. Same mass, opposite charge, born together in every single reaction. And matter and antimatter cannot coexist. The instant a particle touches its antimatter twin, both are destroyed completely, converted entirely into pure energy. If the early universe had made equal amounts of both, they would have annihilated each other almost immediately, leaving behind nothing but light. No atoms, no stars, no galaxies, nothing solid at all. But that's not what happened. For every roughly 1 billion matter-antimatter pairs that should have annihilated perfectly, one extra particle of matter was left over, with no partner to destroy it. Everything you see, everything that exists, is made up of that tiny leftover surplus. We are the rounding error. This isn't a philosophical puzzle. It's a real, unsolved gap in physics. Neither the standard model of particle physics nor general relativity, the two most successful frameworks we have, predicts why that imbalance exists. By every equation, the surplus shouldn't be there at all. In 1967, physicist Andrei Sakharov worked out the conditions any explanation would need to satisfy, and one of them is the strangest. Matter and antimatter have to break a symmetry called CP symmetry, decaying at very slightly different rates. Without that difference, there's no way to end up with more matter than antimatter, no matter what else happened in the early universe. The good news, that kind of difference is real, and physicists have actually measured it. In the 1960s, experiments studying particles called kaons found the first evidence that matter and antimatter don't always behave identically. It was later confirmed more precisely in the 2000s using particles called B-mesons. CP violation is not hypothetical. It's a measured, confirmed phenomenon. Here's the catch. When physicists calculate exactly how much matter that known effect could have left over, the number comes out far too small, by many orders of magnitude, to explain the universe we actually see. The known source of CP violation is real, it's measured, and it's nowhere near enough. In March of 2025, researchers at CERN's LHCb experiment reported something new. The first ever confirmed observation of CP violation happening in baryons, the category of particle that includes protons and neutrons, not just the lighter mesons studied before. The result was statistically strong, and it's a genuine, recent addition to the picture. But be clear about what this does and doesn't do. This new measurement is still far too small on its own to account for the cosmic scale imbalance. It doesn't solve the problem. What it does is confirm that this exact kind of effect is real in more places than we'd previously measured, narrowing where a fuller answer might be hiding, without providing that answer yet. There's a second, completely different lead being chased in parallel. Experiments called T2K in Japan and NOVA in the United States are searching for a similar asymmetry, not in quarks, but in neutrinos, the ghostly particles that barely interact with anything at all. If neutrinos turn out to violate this same symmetry more strongly, it could point to an entirely different mechanism, called leptogenesis, working alongside or instead of the quark-based explanation. Early results from these neutrino experiments have hinted at a meaningfully large asymmetry, exactly the kind of thing this problem needs. But the data isn't precise enough yet to call it confirmed. It's a promising lead, not a finished answer, and more data is actively being collected right now to settle it. If either lead eventually pans out, quarks or neutrinos, it would mean physicists have finally identified the actual mechanism that let a universe exist at all, instead of one that erased itself in its first fraction of a second. If neither one turns out to be big enough, it would mean there's a source of a symmetry we haven't discovered yet, hiding in physics beyond our current theories entirely. For now, the honest answer is that nobody knows the full mechanism. Real progress has been made, confirmed CP violation in kaons, in B-mesons, now in baryons, and a live, actively tested lead in neutrinos, but none of it adds up to the total asymmetry the universe actually shows. The gap between what we've measured and what we need is still there. Every galaxy, every star, every atom in your body exists because of a tiny imbalance physicists still can't fully explain. Does it change how you think about your own existence, knowing it comes down to a rounding error in the early universe? Let me know in the comments. New discoveries unlocked daily. Subscribe so you never miss one.